Hello guys, Dr. Hasbullah here, and in this video we're going to continue our discussion on the isentropic nozzle flow. Previously we have derived the equation where we know the relationship between area and velocity when Mach number changes. So basically in subsonic flow, when Mach number is less than 1, when the area increase, velocity will reduce. But when Mach number is greater than 1, meaning in supersonic flow, when the area goes up, when the area gets bigger, the velocity will also increase. This means that if you want to have the flow to be supersonic, then you need to have a converging and diverging nozzles. Okay, so basically a converging nozzle will increase the velocity when Mach number is less than 1. But when Mach number is 1 and Mach number is going to go greater than 1, you need to increase the area so that you have the supersonic flow. Now let's say that you have a reservoir, okay? And in order to make the flow inside this reservoir go supersonic, you need to have a converging and then a diverging duct. Okay, so in this reservoir, I'm going to have pressure O, PO, TO, and also rho O. Okay, so basically O indicates that this is a stagnation condition whereby the velocity of the air inside the reservoir is not moving, right? So VO is 0 meter per second. Okay, and I'm going to define a few parameters here, especially in the nozzle bit. Okay, so in here we call it throat. Throat is the area with the smallest cross section inside the nozzle. Okay, and this is the section of converging nozzle. Okay, so basically what happens when the nozzle is converging is that the dA is less than 0. Okay, the change in area has to be negative because it's a converging nozzle, right? And then the velocity, when dA is negative, the velocity will always increase. Okay, the velocity will always increase because the Mach number is still less than 1. The flow is still accelerating to Mach number equal to 1. Okay, but when Mach number equal to 1, which happens at the throat, okay, so at the throat, the Mach number becomes 1. Alright, and to make the flow go supersonic, which means Mach number more than 1, what you need to do is to increase the area. That's why you have the diverging section of the nozzle. Okay, so this is diverging nozzle. Okay, whereby the dA here is positive. Okay, meaning that the area is increasing. So when Mach number greater than 1 and dA is positive, you will have positive dV. Okay, and of course here is Mach number greater than 1. And just to be clear, the flow is going from left to right. Okay, and this is exit or E. And if I take the energy equation between 2 points and assuming there is no work and no heat, okay, so W dot equal to 0, there is no work and no heat transfer, meaning the system is adiabatic. Okay, so there is no Q. Alright, so what I have on the left hand side is actually 0 is equal to V2 square minus V1 square over 2, right? That's the change in kinetic energy, plus H2 minus H1. That's the change in enthalpy. Okay, and I'm just going to assume there is no potential velocity change because our nozzle sits horizontally, so there's no difference in Z direction. And if I rearrange this, I'm going to get V1 plus H1 equal to V2 square over 2 plus H2. Alright, now I want my point 1 to be inside the reservoir, right? And point 2 is anywhere inside the nozzle. Okay, so what happens is that you know that in the reservoir, V is 0. Okay, so I can cancel this out. Okay, so what I have is H naught equal to V square over 2 plus H. Right? And remember, naught is the condition in the reservoir. It's a stagnation condition whereby the flow is not moving. Okay, so H naught can also be written as Cp T naught equal to V2 square over 2 plus Cp T. Okay, does it make sense to you? Right? And I'm gonna do a bit of manipulation here, right? Using what we already know about the ideal gas equation. Okay, so we also know that the speed of sound, C, is equal to square root of KRT, right? And this gives us C square equal to K times R times T. Okay, I'm just going to write this equation again here. So CP T naught equal to V square over 2 plus CP T, right? And we know that M, which is Mach number, is the ratio between velocity and speed of sound. Okay, so V is C times M, right? And I'm going to replace it here. Okay, so what I have here is CP T naught equal to M square C square divided by 2 plus CP T. Now that I have this equation, I know that C square is actually KRT, okay? And I'm just going to put that into the equation. This is M square times KRT divided by 2 plus CPT. Okay, this is equal to CPT naught. Alright, and what I'll do next is I will multiply everything with 1 over T and bring the CP from the left to the right hand side of the equation. So the left hand side, what you have is T naught over T equal to M square over 2 KR over CP plus 1. That's what you have now, and we also know that R equal to CP minus CV, and that CP over CV is equal to K. So if I replace R with this equation, I will end up with equal to M square over 2 K CP minus CV over CP plus 1. Right? So this means M square over 2 K 1 minus 1 over K plus 1. And this will become quite easily. I'm going to put 1 in front. So this is 1 plus K minus 1 over 2 times M square. Okay, and this is equal to T naught over T. Alright, and this is the relationship that we are looking for, especially for temperature. So what you have now is the relationship between the reservoir and the condition inside the nozzle. So whenever you know the Mach number, okay, you will know the ratio between temperature in the reservoir and the temperature in the nozzle. And we know from the relationship before that is T naught over T equal to P naught over P K minus 1 over K, and also P naught over P equal to rho 2 over rho 1 to the power of K. Okay, let me check it again. If we have that equation, I believe that we do. This is addressed in the very beginning of the compressible flow chapter. Okay, so this is the relationship that I've written here. Now I'm going to express P and rho, the relationship between P naught and P and rho naught and rho, in the form of Mach number, and it's not that difficult because we already have this equation, right? So P naught over P is simply 1 plus K minus 1 over 2 M square, and this will be K over K minus 1, right? And rho naught over rho will become 1 plus K minus 1 over 2 M square 1 over K minus 1. Right, so you have now the three very important relationships in the study of compressible flow, which is relationship between the condition inside the reservoir and the condition in the nozzle. Okay, regardless whether it is temperature, pressure, or density. So basically what we have here is that the Mach number will increase as the flow goes. right? But one thing for certain is that at the throat region, the Mach number will always be 1. It's because that at the throat, okay, there is no change in area, isn't it? Right? When there is no change in area, this relationship dA goes to 0. And that is where you get M equal to 1. Mach number equal to 1 only at the throat. It cannot be anywhere else. Now, coming back to our equation just now, what happens to this relationship? Okay, T naught over T, P naught over P, and rho naught over rho, if Mach number equal to 1, and let's assume that the medium is air, right? So K is usually 1.4. It's a safe assumption, right? And this means that this condition is happening at the throat. We agree that Mach number 1 can only be at the throat. Okay, and if we put this information inside the relationship, what you have here is, let's say at throat, I'm going to use asterisk. That means T throat, temperature at throat is this, T asterisk. Okay, pressure at throat is P, and rho at throat is that one. And if I put this into the relationship, so I will end up with T naught over T asterisk, okay, equal to, right, just put K equal to 1.4 and M equal to 1, you will have 0.4 divided by 2 plus 1. Alright, so that is 1.2, meaning that the temperature at the reservoir, okay, the temperature here at the reservoir is 1.2 times higher than the temperature at the throat. That is what it is, okay, as simple as that. Okay, usually we write this in such a way that we do T asterisk equal to 0.8333 T naught. Okay, so I'm just going to write the P asterisk here. Okay, so P at the throat is actually 0.5283 P naught. Okay, and also rho at the throat is 0.6340 P naught. Okay, now this is, for me, I think this is an excellent relationship. And it's quite easy to get a sense of what this relationship means, okay? Let's say I take pressure and I want to build a device that is capable to generate a supersonic flow, okay? So what I need to make sure is that the pressure of that device has to be able to generate this ratio, okay? And when I get this ratio, I know that at my throat, okay, I have Mach number equal to 1. And if I expand the nozzle after that, I know that I'm going to continue to get supersonic flow. Alright, so I would say that these three information, okay, these three relationship is a very important relationship in fluid mechanic compressible flow, especially when you are dealing with air. And when you design something, and if you want to take it to supersonic level, right, you need to make sure that these parameters are achieved. Okay, otherwise, if you have the pressure that cannot support this ratio, for example, then you simply will not have supersonic flow. With that relationship, I will end the video here. So try your best to derive the equation and recreate this relationship, especially this equation. And once you do that, you can move on to the next video where we will discuss further and I will show you graphically what does this relationship means. So thank you for listening and I'll talk to you soon. Bye.